Okay, this is, if you like, a quick recap on limits. Okay, limits we did in calculus, you've been exposed to them before. You should, I suppose, they're ones that you would have revised over as well. So they should be a little fresher maybe than some other things. But just to go back over it nearly fresh, a limit is the value that a function approaches as the input approaches a particular value. So what we looked at, I suppose, in the first place was maybe cases where we might look at a function and say, well, what's going to happen to my function as x goes towards a particular value? So maybe as x goes towards like 4, where is my function going? As x goes towards 6, where's my function going? And then we would have looked at limits to infinity then. As x goes towards an infinite number, where will my function kind of converge to, or where will it approach to? And not all of our functions had a limit, had kind of a defined limit, and it all kind of depended on, I suppose, the particular function that we have. The same is true of our sequences. So as the number of our terms in our sequence becomes very large, what we say is the values may converge to a limit. And the limit is this unique number such that my sequence, my Tn, converges to L as n gets larger and larger. So the same kind of, I suppose, notation that we had for our functions. The limit as n goes to infinity of Tn is L, where L is this kind of number that we're converging to. And kind of reminding ourselves of, this is kind of the main rule we're going to be using here, is as the limit as n goes to infinity of 1 over n to the power of p, so any sort of power where so long as p is bigger than 0, a fraction as n gets bigger, that fraction itself will get smaller. Because the denominator is getting bigger, the fraction itself is getting smaller. So what we would have seen before as well is that when we take those limits, because the fraction is overall getting smaller, it's getting closer and closer and closer to 0, such that we say that the limit is going to be 0. If a limit exists, we say the sequence is convergent. And if it does not exist, then we say it is divergent. So in terms of kind of what those words even kind of mean, if things converge to something, it means they kind of are approaching. So all of those arrows you could say are kind of converging on that one point. Diverging means they're going the other way. So two arrows there diverging, they're going in opposite directions. So a limit, you can kind of think about it, it's one of the more logical uses of words there really in terms of the things that we've done. Convergent, it's going towards that limit. If not, it's going to be divergent. It's never going towards any sort of limit really. Looking back at kind of the general properties that we have for limits, the limit, if I have two sequences here, for example, that have limits, which are L and M, the general properties we have there would be the limit of a constant is a constant. So because there's no n part there, constant is just stays as a constant. As n gets bigger, it just stays as a constant. The limit as n goes to infinity of 6 is just 6. 6 just stays as 6. If we have a sum of two sequences that both have a limit, then the limit of the sum is the sum of the limits. So instead of saying the limit of Tn plus or n, I could say the limit of Tn plus the limit of or n. Same is true for multiplication, same is true for division. Okay, so all of these kind of, I suppose, operations can kind of be nearly isolated, I suppose, from our limits here. And sometimes that allows us to kind of compute those limits a little bit easier. One of the other ones that we see as well is to do with square roots. And we'll see that in some of the examples as well, whether our square roots can kind of be nearly incorporated or our limits incorporated into our square roots to some extent there. But just getting kind of stuck into some of our limits here, we're not going to spend an awful lot of time on this because I suppose you can kind of go back to calculus where we maybe went into a bit more detail in terms of these limits anyway. But looking at the limits of a sequence here, evaluate the following limits. When we have a function of this format, we want to make use of that rule that we had with the fractions. And in order to do that, we need to give ourselves some more fractions to work with. And we essentially want nearly every term to have some sort of fraction in it. So we pick the highest power of our variable there, which is n to the power of 3 in this one, and I'm going to divide each term by that n to the power of 3. So n squared divided by n to the power of 3 is going to give me n divided by n to the power of 3 gives me n squared. 1 is going to be over n cubed now. This is just 1, and this is 2 over n to the power of 3. And what that means for me now is as n goes to infinity, I know that each of these in turn is going to go to 0 because they're a fraction of n. That denominator is going to get bigger and bigger and bigger and bigger and bigger. So the overall fraction will get so small that it's nearly that it has a limit of 0. It's essentially approaching 0 over 1 plus 0. So we essentially get 0 over 1, which of course is just 0. Okay, and that is, we are allowed to have 0 on the top of our fraction there. Looking at the second one, we're going to make use of one of our new rules. So the limit as n goes to infinity of 2n plus 4 over 5n minus 3 plus the limit as n goes to infinity of 2 over 2n plus 4. So splitting out my limits there, hopefully to make it a little bit easier for myself. Next, I'm going to use the same rule that we just used there, dividing by the highest power of n in the fraction, which in this first one is just n, and similarly in the second one is just n. And evaluating those limits is going to give me 2 plus 0 over 5 minus 0 plus 0 over 2. And that's just going to be 2 over 5 plus 0, which of course is just 2 over 5. The last one, I suppose, is the most interesting really here in terms of my limits. And what I can do is I want to try and incorporate that square root to the whole fraction, and then I'm going to see, can I bring my limit inside of that as well? So in terms of, or in order to kind of bring that square root over all of it, I'm going to have to square the bottom side here as well. So 7x plus 5. We're going to write that as 7x plus 5 all squared, so that I can take a square root over the whole fraction there. And that kind of means that I haven't changed the meaning of my fraction. I'm just making use of kind of my indice rules there nearly more than anything else. Next, I'm just going to multiply out that bottom bracket. So x squared plus 3, and on the bottom I'm going to have 49x squared plus 70x plus 25. Now what I can do here as well is, because I'm taking the limit of a square root, that's going to be the same as the square root of the limit. I can actually incorporate my limit underneath my square root here. And it's a handy trick for ones like this, because you can be quite unsure of whether that's still going to apply here, but it is going to apply. Okay, so the square root of the limit is the same as the limit of the square root. So following the same kind of rules or logic as before, we're going to divide by the highest power of x. So that's 1 over 3x squared all over 49 plus 70 over x plus 25 over x squared. Each of those terms that has an x squared on the bottom is going to go to 0 when I evaluate my limit. So 49 plus 0, so I get root 1 over 49, which of course is just 1/7. Okay, 1 over 7. So evaluating my limits there, hopefully a quick kind of recap of the rules that we hopefully should be a little familiar with, and if not, are kind of getting more familiar with, particularly looking here, I suppose, just at limits to infinity. Now the one last little bit to look at is just a general idea on kind of partial sums and kind of smaller sums within my limits here. And if we have an infinite sequence of numbers, we can write those as a1, a2, a3, a4, where they're just kind of terms, they're just kind of numbers in my sequence here. And we might form that then into an infinite series by just taking a sum to infinity, so adding an infinite number of those individual terms. If we then think about what we call partial sums, that would be me adding smaller amounts of those kind of individual terms. So S1 being A1 plus just A1 on its own, S2 being adding the first 2 terms in my infinite sequence, S3 adding the first 3 terms in my infinite sequence. And what we've done is we've formed a new sequence which is made up of each of those partial sums. So we have S1, we have S2, we have S3, and this is kind of an individual sequence in its own right. If we take the limit of that sequence, we can find what we call the sum to infinity of the sequence. And that's by taking the limit of essentially my Sn. If I continue coming up with these partial sums and want to see where does that sequence end up, what's kind of the last value in that sequence, how many terms can I add up before I just kind of stop, before it's done, I'm going to take the limit. I'm going to see how far can n go. If n goes to infinity, what would that total sum look like? And that's kind of where we end up with the sum to infinity of these kind of partial sums, of these kind of all these different additions of those A1 terms, just those different terms in the sequence. If I take that sum, that's the same as me taking the limit as n goes to infinity of Sn, where Sn is generally my sum, my partial sums there. And we see Sn used for the series as well, so we're kind of drawing that comparison there. And we're going to see that then in the geometric series as well, and how that kind of plays a role in the sum to infinity of those as well. But just kind of being aware here across the board of kind of how we can take infinity and kind of use that with our sequences and with our series here across the board, and how it kind of plays a role in those, and kind of, I suppose, just making use of those general rules that we should be making ourselves familiar with And the main thing really besides all of that is really just the idea of sequences being convergent and divergent and what those words mean, and just recognizing that idea.